Hi, thank you for listening to my presentation. This will be about the science of cabin pressure. Let's start off with a little story. You were just contracted by Boeing to design a new plane. While designing your prototype, you dismissed the idea of cabin pressurization, since you do not think it's very important. On the first flight test of your plane, you decide to take the initiative and fly the plane yourself. As you increase in altitude to 100,000 feet, you start to feel lightheaded and pass out. So after listening to the previous story, you might be wondering, what exactly happened? Well, basically what happened was you lost oxygen due to increasing in altitude without any pressurization in the air. And that is because when you increase in altitude, the density of air particles, dramatically decreases. Um, which is like far lower than your body needs to operate functionally. And the reason why there's less density in the entire air up higher is because of lower pressure and higher volume of air in these high altitudes. And so Boyle's law was discovered by this guy named Robert Boyle. He is considered now as the first modern chemist in history, and he discovered the relationship between volume and pressure, and they have an inversely proportional relationship. So on account of Boyle's law, we have a Boeing 747-40F with a volume of around 755.1 cubic meters, and that roughly translates to 755,100 liters of air. And so right now, at sea level, there's air pressure of around 14.7 psi, and the air mass inside the Boeing 747 is 920.85 kilograms of air. And 30,000 feet in the air, there's an air pressure of 4.3 psi, and a volume of around 2,581,388 liters of air, and around the same mass as down below at sea level. So you might be wondering how I got the numbers from the previous slide. Well, I used Boyle's law and times 4.7 times 755 and 100 liters to and then divide that by 4.3 psi, the air pressure at 30,000 feet in altitude, to get 2,581,388 liters. And then, we're finding the mass. I found out that 1 kilogram of O2 would equal 820 liters. So by dividing the volume of the cabin by 820, I would get 920.85 kilograms of O2. And using that number, 920.85 kilograms of O2 and 755,100 liters of O2, I found the density of oxygen of 0.001 kilograms per cubic meter at sea level. But at 30,000 feet, I used the same method and I got 0.0003 kilograms of O2 because of the increase in volume because of Boyle's law, which means that air is so sparse that it's not hospitable for life. So you might be wondering how we need to solve this problem. Well, engineers have become very creative for this. So basically, they've used the turbines on planes to actually capture air while flying and pressurize it and spew it into the cabin, basically making up for the excess volume in the air by increasing the density of air inside the cabin, making the pressure similar to on sea level, and basically making it able for us to survive up in the air. And all the excess air that's flown into the cabin gets spewed out through a valve, which closes once the pressure reaches a level which is stable for comfortability. So these are my sources, and thank you for listening to my presentation.